The last model which we cover in today's lecture is the so-called vertex copying model. And again, it starts from a motivational example in which we can claim that researchers who are into paper writing, scientific paper writing, they are sometimes or many times they are copying citations from bibliographies of papers they basically read. And Kleinberg and his collaborators, they have proposed an alternative mechanism for network formation, which takes this idea and adds a further step to it. And the idea is that that if so in the setup, if we imagine that all the researchers they would just take the bibliography, so the list of references of papers they read, then basically the whole procedure would not be really creative, because I mean from the network formation point of view, because then the new paper would get the same kind of out degree, and not only in terms of number, so like the out degree as a quantity, but also qualitatively would make the same pattern of outgoing edges as the vertex which they copied the references. And a little bit of a modification would give us a proper model, surprisingly, which can give rise to a power law degree distribution. And of course, it's I mean correct to say that that the original idea that everybody just copies blindly everything from the papers they read, it's absolutely non-realistic, and in this way new papers would never give any chance to be cited. Okay, now a modified approach is the following, that given some fraction, let's denote it by gamma. So by gamma we mean that a fraction of all references we are copying. So let's say gamma is 0.7, then 70% of the references which can be found in papers which we are reading. So we are copying that, but the remaining part, so in this case, in this example, it's 30%. Then we are selecting the other nodes, the other remaining nodes which are not referenced in these papers which we have read. So we are selecting them in a uniformly random way. And of course, we are not citing papers in reality in this way. So we are not selecting uniformly at random, but for the model right now, this is the approach. And we cannot go to the details, but it turns out that the degree distribution of this model is giving a power law degree distribution with the parameter alpha, which is apparently equal to 1 plus 1 over gamma. And depending on gamma, which is of course between 0 and 1, so it's never 0 and it's never 1. In fact, if it's 1, then we get back the same problem that the new papers will never be cited. So it's something between 2 and infinity. So note that by this model we can create or generate such a power law degree distribution network in which the alpha parameter can be set up between 2 and infinity. Well, after this we can maybe argue that, okay, so if this is the case, then well, the vertex copying model maybe can really generate all the networks which are following this preferential attachment attitude. Okay, so then all the networks are identical in every respect to preferential attachment. Well, the thing is the following, that mm, in preferential attachment there is no such thing as this claim here, that most vertices in the network will have connections that are similar to those of at least one or the other vertex. So without any detail, again, unfortunately we can't go into this, but it turns out that there is no such a thing in preferential attachment. So in preferential attachment networks, we don't have this kind of node similarity in the network. And on the other hand, or at the same time, we have seen that by examples that many real networks follow power law degree distribution, and the preferential attachment models can generate such degree distribution. So basically, we can maybe conclude that the real networks are product of preferential attachment processes. And whether this is correct or not, of course, it's debatable. Well, I think this is not correct, but that's my point of view. But anyway, in for example in real citation networks, well, it turns out that there are many pairs of vertices whose outgoing connections are approximate copies of one another. So basically, we could claim after this that maybe the citation network is a vertex copying method, but this in fact is just alone doesn't necessarily imply this claim. Well, and most of the cases we cannot decide which mechanism is closer to reality. And as a final note here is that in some biological networks, biological networks which are following power law degree distribution, and clearly from the how it gets generated in real life, we can really observe the vertex copying mechanism. They are not following the preferential attachment procedure, basically. Well, this last figure is actually a typo in the title, so if we do computer simulations in this vertex copying model and not the price model, sorry for that, then we get such degree distribution functions in which we have very, very similar figures than those which we can do with real world networks. And here on this figure we can see that the circles are following the analytical model, and representing the analytical model, and the straight line, which is completely covered by the circles, that's the numerical model. So basically the two things is overlapping each other. So one can do a very, very nice and very good power law degree distribution networks and numerical simulations using this wonderful procedure.